Helicoverpa armiger and Helicoverpa punctigera are widespread agricultural pests. Helicoverpa will hatch from an egg that the moth will have laid on the leaf, branch or on the inside of a square, which is a young and immature bulb. Once hatched, these little critters, whilst in the larva stage, will eat the fleshy green leaf on the plant, but will inflict the most damage when they start to eat through the cotton bolls. This is where you start to see boll rot occur and cotton bolls will start to drop off the plant. If these bugs were unattended and not controlled, could signify serious issues to our Australian cotton industry and would see a huge loss in cotton production. This issue had to be dealt with, which led to the introduction of Bt cotton. In 1996, the single toxin Bt cotton, known as Ingard, became available to the farmers. Ingard entailed the new Cry1AC gene, which provided a good quality of control of the targeted Helicoverpa species in younger plants. However, as the plants began to mature, the titer of the Cry1AC gene declined, meaning the larva could survive on the more established plants. Due to this issue, a new technology was released in 2004. Ingard was replaced by Bolgard2, which entails the Bt genes of Cry1AC and Cry2AB. These two genes expressed in Bolgard2 have provided a more consistent and stable control. However, in the absence of the Cry1AC gene later in the growing season, as was seen in Ingard, seemingly there are opportunities for selection of Cry2AB resistance, therefore meaning that susceptible larvae can occasionally survive and pupate under Bolgard2. Figure 1 enables us to see how important and popular Bt cotton became, as it made and is making the control of Helicoverpa so much easier. Figure 2 shows frequencies of Cry2AB resistance in alleles in H. punctigera. The values in parentheses below the years show the number of resistance alleles out of the number of alleles tested. Along with the systems such as Bolgard2 and the refuge crop practices, companies were still trying to limit the amount of resistance issues Helicoverpa were carrying. This led to Monsanto in 2009 announcing the development of their third generation Bt cotton, generally Bolgard3, which utilises the Cry1AC and Cry2AB genes, along with the new VIP3A gene added to the two other toxins. The frequencies of the VIP3A resistance alleles in H. punctigera determined from F1 and F2 screens are not considerably different and indicate the level is 0.011. The efficacy of the VIP3A gene also declined as the plants matured and the season progressed, however not to a certain degree as the Cry1AC gene in Ingard did. Ideally, future generations of Bt cotton should express high titers of all genes throughout the entire season. Present variability in the genes in Bolgard2 and presumably Bolgard3 is not ideal. However, the chances of both species of Helicoverpa becoming resistant to more than one of the three toxins within Bolgard3 is extremely rare. Therefore, Bolgard3 and other management practices should nonetheless provide a robust and beneficial technology for the Australian cotton industry. It should effectively control the resistance issues of the Helicoverpa species at present.